The first lecture focused on valence bond theory, and this one will look at basic molecular orbital theory, mainly looking at the homonuclear diatomic molecules. And then the third lecture, I'm going to go and look at some other geometries and some heteronuclear stuff. All right, so there are some problems with valence bond theory. It doesn't explain everything. It can sort of do a good job for geometries, but it doesn't address at all electronic properties, because once you put all the electrons in, the point is that everything is always filled up. So it doesn't explain why oxygen is paramagnetic and nitrogen is not. Or if we look at inorganic complexes like these two cobalt complexes, which are both cobalt +3, so they're D6, for example, right? We have anionic ligands here, and so we have this overall -3 charge, so that makes cobalt +3. And so what we come up with is this D2sp3 hybrid orbital, because we know we have an octahedral shape. We have 6 ligands that are come in. Those are all, whether it's the fluorine here that's negatively charged, has a lone pair, or has it's a Lewis base that's donating both electrons, or the ethylene diamine, same thing, that's a neutral donor, but at the end of the day we have 2 electrons that are donated into an empty hybridized orbital. So when we put all those electrons in, which we usually don't do, everything's paired up, and we don't know why this one is diamagnetic and this one is paramagnetic, because paramagnetic implies that there are unpaired electrons somewhere. So that's a deficiency. The other thing that valence bond theory doesn't do very well is address more than 2 atoms, right? Because we're always looking at a single atom, and usually the central atom, but it can be, if we're looking at longer structures, whatever that is, we can look at each carbon, each single atomic orbital separately and come up with a hybrid orbital for each. But molecular orbital theory has an advantage because it can look at it looks at a linear combination of atomic orbitals. So it takes 2 atomic orbitals and makes a molecular orbital set. So we actually have a lowering of the energy and an increase of energy. We have contribution to bonding, which is when we are lowering the MO, and there's some for every MO that goes down in energy, we have an MO that goes up in energy, and that doesn't contribute to bonding. So it looks at it slightly differently. So there's 3 possibilities for MO theory. One is bonding, and it's essentially the same thing that we do for valence bond theory. If we have direct overlap, whether it's side by side pi, or direct overlap, as we see here between this p and this d orbital, direct overlap or side by side overlap, that leads to bonding and lowering of the energy of the molecular orbital. And but we also have 2 scenarios. We have anti-bonding and non-bonding. So for anti-bonding, we have a negative overlap of the p orbitals, so which is here kind of shown not very well, right? We have the positive and the negative lobe of a p orbital, and that actually creates electron density or regions that are away from the bond. Okay, and those are called anti-bonding, and they usually get that star. We can have pi star and sigma star, and those are anti-bonding regions. And then we have scenarios where we don't have orbitals that have the same orientation or the same energy, so they simply don't overlap at all, and those are non-bonding regions. So those are the 3 scenarios that we have. Looking at a very simple set here, just for dihydrogen, we always have the atomic orbitals here on the left and the right, and then what we show in the middle are the molecular orbitals. And so for the 2 s orbitals, we get a sigma and a sigma star. So we have a bonding region and an anti-bonding region for the molecular orbital theories, and there are some great pictures of that. So that's positive overlap, and that's negative overlap. So that's destructive interfering here. So, so for the sigma component here, and that's what's shown here. So this is the sigma, and this is the sigma star. This region leads to bonding, right? Lowering, again, the potential energy. So we've got the 2 valence electrons from the atomic orbitals, you put them in, and so you get a sigma bond. You can also calculate bond order here. I have a formula in a second. But what is new here is this anti-bonding region. So we have this area here that is the lowering in, and then we have also regions that are away from the bond here, right? And so they don't contribute to bonding. So we can actually put electron density in there, and we can still have bonding. But when all of this is full, we don't really have bonding, right? So this is just a picture. This is another picture, just a different representation of the bonding and the non-bonding regions of the MOs. And so here you can also see this one is contributing to bonding. So we have lowering of the energy, and again we use star and just sigma, and then the star indicates a non-bonding area. A couple of other things, you can calculate the net energy change, and as long as that net energy change has a value other than 0, we do still have bonding. And we can calculate the bond order by taking all of the bonding electrons and subtracting them from the anti-bonding electrons and dividing by 2. So all of those sigma and pi molecular orbitals are bonding, and all those with stars are anti-bonding. So in the case of dihydrogen, we would have there's 2 bonding electrons, 0 anti-bonding electrons. So that would be a bond order of 2, which we would also expect from drawing the Lewis structure. There's a single bond that has a bond order of 1. So that's an important formula. You'll be asked to calculate that undoubtedly, no matter who your professor is. So the bottom line here is that you have to have the orientation of the orbitals. They have to face each other, and so that we can have some sort of overlap, right? Whether it leads to a destructive or a constructive region for bonding, as long as they overlap, that's important. And they have to have similar energy level of the atomic orbitals, right? So and then a net energy change overall, right? So bonding minus anti-bonding has to lead to something, not a net change of 0. Then we don't have bonding at all. All right, so the 2 different MO diagrams that we expect for the diatomic molecules of the second period. So we have F2, O2, B2, C2, N2, right? We don't really look at B2 or C2. We can even look at Li2 or Be2, and so that's one of the advantages of molecular orbital theory. We can look at molecules that we can't really draw a Lewis structure for and assess them, the feasibility. So we have, as I said again, for F2 and O2, we have the atomic orbitals here on the left and the right, and then in the middle we show the molecular orbitals. And so the splitting is always, we looked at the S component, we have a sigma and a sigma star, but for the p orbitals here we get different. We have a sigma and a pi component, right? If you think about, now I think I have a better picture here in a second, but if you think about, we have the 2 p orbitals that face each other if we had a central atom, and that would be the sigma component. And so if you have a sigma component, you have a sigma star component, so one goes up, one goes down, and then the other 2 p orbitals are away from the bond, so that's your pi, and they're degenerate, meaning they have the same energy, they're both at the same orientation towards each other with the same distance here, so they are degenerate, they have the same energy. So but that also leads to a pi star. And then what happens for lithium, for Be2, C2, and N2, there's that crossover for F2 where the pi and the sigma are reversed, right? So here we have the sigma and the pi. The pi is lower than the sigma, and so this is something that you need to remember. And so why is that? Well, that is because you go back to electronic configurations and the ground state energies. You might remember that as you fill electrons into your orbitals, whether they're atomic or molecular, that we are going to look see a lowering of these orbitals, right? So at some points when you populate the 3D orbitals, they drop lower than the s, right? That's our ground state for transition metals of the fourth period. We had the 3D switch with the 4s in energy, and so that similar phenomenon here for the diatomic. So here are all the MO diagrams for the uncharged diatomic molecules from Li2 to F2. So we're not shown the atomic orbitals, right? We're only shown, this is only the center, the MO in the center, and so we have this. So from the from the S component here, right, that would be the 2s. Here's that split. We have sigma, and then this would be the sigma star here. And then for the P component, we have the pi and the pi star and the sigma star. So that's what these are. And so if you start with Li2, the pi is lower. And then as we fill in electrons, you can see here, right? So the sigma lowers in energy. This is just a little lower for Be2. And then for B2, it goes lower and lower and lower. So it doesn't have an effect for the s electrons here, or the s atomic orbitals. But it does make a difference for the pi and the sigma of the p orbitals, right? So once you can see that the lowering of the energy, so once you get to dinitrogen here, you are lowering the energy of the sigma here, and once you get to oxygen, you have enough energy where the sigma and the pi actually reverse. So here you see for O2 and F2, you have your sigma that's lower than your pi. But here, this is a great picture of the anti-bonding and bonding regions of the 3p orbitals here, right? So we have for the pi, we have the bonding model. So this is the side-by-side constructive overlap. But then we also have a pi star. That's the one that goes up. There's electron regions that are away from the bond, so they would not, if you put electron density in here, right? So, and what do you know? We have carbon monoxide that was doing, those are the carbonyl bonds, right? They were doing pi back bonding, right? So that pi back bonding took place between the transition metal electrons and a pi star, right? So you've got a pi, this shouldn't be full, but you've got a pi star orbital that's pointing away from the bond. So you've got this transition metal coming in with its electron, and it donates density into that pi star orbital. So that can start explaining some of the pi back bonding and how that happens, and that you just can't do that with valence bond theory. And then we have, of course, the sigma component here, direct overlap of the 1p that points towards the other bond. And so there's obviously similarities towards with valence bond theory. But so this is just, again, another picture. This is the px that directly faces the other x orbital. And then here are the two degenerate p orbitals that do side by side. And so we have contribution of, so these two are going to show up together as the same energy level, and then the pi stars are going to be up here. They also show up together. They have the same energy. Let's just use this. Let's do, just for fun, let's do N2, right? So might as well. Nitrogen has 5 valence electrons, so 1, 2, 3, 4, 5. The other one, 1, 2, 3, 4, 5. That's 10 electrons. We put them all in. 1, 2, 3, 4, 5, 6. We follow Hund's rule, right? We spread them out, and we pair them up. And so this would be the model for N2. We can then calculate the bond order. We have 6 bonding electrons, and we have no anti-bonding electrons, and we divide that by 2, and we get to a bond order of 2. Everything is paired up, so it is diamagnetic, but we also have vocabulary here. So the energy transitions would take place between the highest occupied molecular orbital, which is the sigma here, right? That is the highest in energy that has electrons in it. So we call that the highest occupied molecular orbital, the HOMO. And then it can promote electrons up to the lowest unoccupied molecular orbital, so that is the LUMO. And so and maybe you took analytical chemistry and you talked about the band gap or the HOMO-LUMO gap, and that's exactly what this is here. This is where all of the energy transitions take place. To this vocabulary slide, so this is just for you to know, so you understand what HOMO and LUMO means. And then degenerate orbitals, the pi and the pi star of the p component was degenerate. They had the same energy, so pretty simple. Okay, so we are ready to practice. Draw the MO diagrams for F2, O2, and B2. We just kind of did it for N2, right? And so let's just practice that, determine bond order, and then tell me if it's diamagnetic or paramagnetic. Pretty simple. So for F2, we need to remember that to use the correct diagram. So F2 and O2 will have the sigma here lower than the pi, and then if I go to N2 or B2 or Li2, the pi and the sigma simply reverse. This is what you will have to remember. I'm not going to remind you, but it's pretty simple. All you do is you can label this. This is the atomic orbital here, fluorine and fluorine. This is neutral, so we have 14 total valence electrons, right? 7 from each atomic orbital. You can put them in 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. Those are our atomic orbitals. Here are our molecular orbitals. So we just take those 14 electrons and we fill them into our molecular orbital diagram, and simply going from lowest to highest and spreading them out if we have degenerate orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we do have some anti-bonding electrons, but it doesn't matter. We still have an overall net energy change, which contributes to bonding. And so also here's the HOMO-LUMO gap here, right? So this is the HOMO, and this is the LUMO. So this is where that is, but we can calculate our bond order. You can include these electrons, but it's 2 minus 2, so they cancel each other out, right? As far as bond order is concerned. But we take the bonding electrons, so we have 6 minus the anti-bonding electrons, which is 4, divided by 2, which is of course 1. If you want to include these, this would simply be 8 minus 6 divided by 2, which is still 1, so that's not a problem. So we know from valence bond theory that fluorine has a single bond here, so this agrees, and then everything is paired up, so this would also simply be diamagnetic, right? So let me put in the rest of the electrons just to complete the picture. But so valence bond theory here obviously should agree, and then with the molecular orbital theory. All right, so here it is, cleaner, and the bond order as well as diamagnetic. We do O2, we still have this scenario, and so oxygen has 6 electrons. You just put them in. Let me do something here. All right, so that would be it here, right? So you put all 6 electrons in, 6 for each, right? Fill them up. You end up with a bond order of 6 minus 2 divided by 2, which is 2. That's a double bond. Surprise, surprise. But the one advantage now we have is we do see these 2 unpaired electrons, so we know this is paramagnetic. Alright, so let me go back to this. The reason I left that blank is to show you what happens if we have, let's say, a radical, right? So we could actually have like O2 plus. I might ask you to do that on a quiz. So all that means is that we have one less electron. So we still have, if you wish, 1, 2, 3, 4, 5, 6 for one of the oxygens. And then the other oxygen, 1, 2, 3, 4, only has 5, because now instead of 12 electrons, we have 10 electrons. Do I know which one is which? No, because we are looking at the MO picture, at the resulting picture. But we can definitely, so I'm sorry, this is going to be 11 total electrons. If we have 12 and we have a positive charge, we have 11. So I put them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we can still calculate the bond order. Now it's going to be 6 minus 1 divided by 2, which is 2.5. So now we have a bond order of 2.5, and this is still paramagnetic. So you should easily be able to do this for any of the diatomic molecules I might ask you for, right? I can charge them. I can even have O2 plus 3 if I wanted to. You should be able to do this hypothetically. This is the picture for O2, as it is neutral. And now I'm going to do one example, B2, because just because we do one where the pi star is lower than the sigma. So boron has 3 valence electrons, so we have a total of 6. 1, 2, 3, 4, 5, 6, right? So here's your boron, here's your other boron, and here are your molecular orbitals. So you 1, 2, 3, 4, 5, 6. This would be paramagnetic, and it would have a bond order of 1, right? 2 minus 0 divided by 2 equals 1. So molecular orbital theory predicts that there should be a B2 possibility, paramagnetic. So not too bad, right? So what happens when you put two atoms together, make a bond with them that don't have the same energy in their atomic molecule, energy for the atomic molecules, atomic orbitals, sorry, not molecules. All right, so here the hydrogen has drastically higher energy than the 2p. We do know that hydrofluoric acid exists, right? And so we do have a sigma and a pi, but we have two p orbitals that simply don't have any overlap. So these are non-bonding here. So we have 4 electrons in the non-bonding region, and then we do still have a single bond, right? Because we don't subtract those, we just do bonding minus anti-bonding, so 2 minus 2, and because the energy is so drastically different, it also can imply that this is highly polarized, and we know that hydrofluoric acid is a weak acid, so this can dissociate because of the polarization. Here's the example of carbon monoxide. So this is a little bit exaggerated, but the carbon atom, the carbon atomic orbitals are slightly higher in energy, have fewer electrons, right? And so we get a picture that is very similar to what we would expect for C2 or for N2. We have the pi that's lower than the sigma, and so the pi back bonding occurs. We have an empty pi star orbital, so we can put electron density in there from ligands, or not ligands, but from the metals. So that's important. If that was full, we couldn't have pi back bonding. So of course we like to look at bigger pictures and also something that's more graphical, so we can tell. We know benzene, for example, has pi clouds, has delocalized electrons. They move around, and so it's kind of nice to look at these calculated pictures. It gives you a better idea of why and how that works. And I don't want to drag these out. Here's ozone. You know, we can say there's resonance here, and we can even go as far as saying, okay, so this is really kind of like this, but this is still a much nicer picture for us to look at. So okay, so that's something completely different. Anyway, this is the end of that. When we come back, I'm going to look at square planar and octahedral and trigonal bipyramidal molecular orbital models.